Hello, everyone. I'm Garud Iyengar. I'm here to talk to you about our project, Economics of Permission Blockchain Adoption. And let me begin by thanking the Data Science Institute, Columbia Engineering, this Columbia-IBM Center on Data Transparency and Blockchains for their generous support for this research. This support has helped us recruit a PhD student, Wenjun Wang, who played a very important role in all the results that came out in this particular project. My collaborators on this project are Jay Sethuraman from the Industrial Engineering and Operations Research Department at Columbia, and Professor Fahad Saleh, who is at the Wake Forest University in North Carolina. So let me try to motivate the research, and then I'll give you some of our results and tell you where these results have been published and what we're going to do further along. And if you have any questions, I'm happy to answer them. So blockchains, I don't have to convince this audience, is an ideal data structure for information sharing. There are immutable entries. You can do privacy preserving operations. They're distributed. What could be bad about them? It looks like they are a platform for making sure that information gets across to people who need them. They can make use of it in the best possible way and do it in a privacy preserving manner. The big problem are incentive issues. So if all the entities on the blockchain were controlled by one particular decision maker, life is very simple, and there are benefits that accrue to this decision maker. But often on a blockchain, we are trying to bring together people who have different incentives and pool their information together. So what might happen is that overall the system benefits, but each entity does not get a fair share of this benefit. And as a result, there could be adoption failures. We identify one such adoption failure in the research that I'm going to delineate in the next few slides, and provide a resolution. So the project, we sort of started off by trying to identify the minimal system where we would see a situation where a blockchain enhances welfare, and yet the players will not adopt the welfare because there are multiple players with different incentives. So here's the structure. Let me motivate the problem that we are after with a simple toy example. There is a game where there are 3 agents, but only 2 players. The difference between an agent and a player is an agent is an entity who is able to enjoy welfare. A player is an entity that takes decisions. So the 2 players can either adopt or not adopt the blockchain. In this setting, if they both adopt the blockchain, then you end up getting a utility of -1 and -1 for each of the 2 players, and a utility of 4 to the third agent that is not a player. If one of them adopts and the other one does not adopt, then the cost of the adoptee becomes 1.5, and the benefit to the third agent becomes 2, which is lower than what they would have gotten had both of them adopted. So the unique equilibrium in this setting between the 2 players that are going to make the decision of adopting or not adopting happens to be don't adopt, don't adopt. That means you end up in this yellow cell. And the reason that happens is that all the benefits of adopting this blockchain go to the third player. And all the costs of adopting the blockchain go to player 1 and 2. And as a result, we end up into a situation where the players don't want to adopt. And although it's socially optimal for the blockchain to be adopted. So how do we fix this problem? We create a welfare transfer mechanism, a contract that transfers welfare from the third agent to the first 2 agents. So in this setting, what we've done is that we've taken 4 units and 3 units and given it to the 2 players that were making decisions. So their utility earlier was -1, -1. We gave them 1.5 units of welfare each. So it becomes 0.5, 0.5, and 1. Everybody is better off compared to the unique Nash equilibrium, which is 0, 0, 0. And this time around, you end up getting to an equilibrium that is better for everybody. But this was possible only because there were transfers involved. There were contracts between the various entities that are involved in this blockchain decision. So we need some sort of transfer mechanism in order to make adoption of the blockchain socially optimal. So we're going to look at a very simple business setting and take this intuition that we had from this simple game theoretic example to a little bit more realistic. And then I will argue to you that somehow this is generic. So we consider a simple supply chain. There's a single vendor that supplies items to a manufacturer who then sells it to consumers. So here's the setup: a vendor, a bunch of manufacturers, and a consumer. And what we're thinking about is a blockchain which allows the manufacturers to share information. Now, why would they want to share information? Because the vendor occasionally produces a bad batch of products. The quicker the manufacturer is able to detect the bad batch of these products, the quicker they'll be able to recall, the lower will be their reputation cost. The details of the model, exactly what the costs are, how does it all operate, we have deferred it. I'll defer it to the paper. And if you're interested, email me and I'll send you the paper and you can get all the details. So vendor shipments, as I said, could consist of defective products. The example to keep in mind is that a vendor is a farmer. They produce food. The food can get contaminated. These defective items could lead to serious illnesses, and the blockchain enables efficient tracing of these defects and thereby saving costs. Consumers want to produce from highest quality manufacturers, and the quality domain here is slightly different from defect. Quality is packing dates and transportation time, which determine ripeness, identity of the source, so that they can check whether there's ethical standards being met, processing, and so on. The quality does not determine the defect, because if that was the case, the manufacturer would have not sold the item in the first place. So we're looking at a situation where consumers like quality and they go to certain manufacturers to buy, but what they don't know is behind the scene, they're being sold by the same vendor. Manufacturers sit between the vendor and the consumer. They're like the grocers in a food supply chain. The grocers face reputation cost if they sell contaminated food, and therefore having an immutable audit trail going from the farmer to the consumer can help. This can cause, the cost can be identified earlier and recall can be implemented. And this cost saving serves as a key motivation for blockchains. Now the problem is, manufacturers may not want to get onto the blockchain, because if they put their data onto the blockchain, consumers are better able to understand their practices. And as a result, they may be able to better select for quality, and certain manufacturers may not want to allow the consumers to do it. So there are three components to a manufacturer welfare: revenue, attract consumers by signaling quality; reputation cost, minimize reputation cost by detecting defects early; and adoption cost, which is the cost of the IT infrastructure needed to set up a blockchain. So basically, since the manufacturers adopt everything, get all the items from a single vendor, really they want to adopt a blockchain so that they can be, that time to defect can be identified at the minimum of the defect detection time, as opposed to the individual detection time. And this could be seriously different. And as a result, you end up, from a purely reputation cost perspective, you can minimize that by getting onto a blockchain. But the problem is that if you get onto the blockchain, the consumers get to know your quality better, which means that being on the blockchain makes sense for high quality manufacturers, but it may not make sense for low quality manufacturers that already have market share. And that's the tension that we look at this. What are the key results that we end up getting from our research? Blockchain always enhances consumer welfare. There's no doubt about that. What we do find is that a blockchain can actually reduce manufacturer welfare, even if there are no adoption costs. Even if the IT cost of adoption is zero, a manufacturer may not want to get onto the blockchain because it reduces his or her welfare. And the reason that happens is because the blockchain starts to concentrate demand among the high quality manufacturers. So in effect, it increases the market share of each manufacturer, reduces the manufacturer base, so it acts against itself in recognizing reputation cost, in detecting defects early, because now the defect detection is happening over a smaller base. Blockchain adoption may not arise in equilibrium, even when the total welfare of entire society is positive. And this happens because manufacturers make the decision of adopting the blockchain or not. Most of the benefit happens to consumers. So even though the society benefits, it doesn't make sense for the manufacturers to adopt the blockchain. So if you go back to that simple example of the game that I gave you, the two players are the two manufacturers. The third player, or the third agent, not player, who doesn't make a decision, is actually the consumer. All the benefits accrues to the consumer, and unless they're willing to share, the players, which are the manufacturers, will not adopt. And a system of transfer from consumers to manufacturers can resolve adoption failures, and in the paper, we clearly indicate that. By the way, the paper is on SSRN, and at the very end, I'll give you the title. It's basically the same as the presentation. And at that point, you can download it and you can look at the results, and I'm happy to answer questions. Some concluding remarks. We feel that this market failure is generic. In most market situations, what happens is that the information is distributed among various different players. When you aggregate this information, the entire collection of players improves their welfare, but the benefits do not accrue equally to all players. Some might have more information, but get less benefit, and so they're not willing to share that information. Some might have very little information, but end up getting most of the benefit. They are willing to get onto the blockchains, but their information will not be useful until everybody else gets on the blockchain. So we will always need some sort of transfers and contracts in order to share the benefit. And we believe that this is generic, and this is going to be a bottleneck that one would have to get over if we want blockchain adoptions to be much more integrated into the technological space or integrated into the industrial space. Here are some publications that have come out of this. We have presented in 3 different conferences: the Toronto FinTech Conference, the Financial Management Association Conference, and the Crypto Economics Security Conference. We've submitted a paper called The Economics of Permission Blockchain Adoption, which is under review in Management Science. And a preliminary preprint is available on SSRN. I will encourage you to look at it. And if you have any questions, comments, ideas, please feel free to reach out to me. Thank you so much.
Again, welcome to this session on supply chain. What I want to do, I want to present my work done as a part of the IBM Columbia grant awarded under the COVID-19 call for papers. And the objective is to design a transparent food supply chain system where we aim at increasing efficiency and sustainability in the presence of uncertainty. First, I want to discuss the question of supply chain transparency and why this is important. If we look at inefficiencies between producers and suppliers in the food system, we can see that these are quite substantial. In fact, they are estimated to be about 60 billion annually. And we have essentially that the inefficiency range from waste in consumer pricing, carbon footprint, food waste, and also the deterioration of the products due to freshness decreasing over time. Now, the reason why we want to consider the use of blockchain technology is that blockchain might have an impact on the reduction of these inefficiencies because it basically enables information sharing. So we view blockchain as essentially an information sharing platform, which can be used by the firms in order to decide when and how to order, and with the objective of improving the decisions of trades on purchases. And sharing this information between retailer and producers and suppliers on inventory and demand has the objective of increased transparency. So there has been a stream of literature that has looked at the question of how transparency about inventory improves the efficiency of the system. That's an old literature. Here we aim at specializing this particular literature to deal with a very important industry, which is the food industry, and also to consider features that are unique to this industry. Now, what are the key research questions that we ask? The first question that we ask is, okay, does information via blockchain always benefit firms? And how can we deal with uncertainty in the presence of, during the pandemic? Meaning, how can we deal with uncertainty in the demand schedule? and in the delivery time. Like these are typical uncertainties that are experienced during periods such as the COVID-19 pandemic. And what we aim at doing here is to essentially look at a supply chain food system where suppliers and retailers are exchanging goods, and particular suppliers are providing goods which are perishable to retailers. Suppliers and retailers are providing goods that are perishable to consumers. And we want to design metrics which allow us to assess how efficient, resilient, and sustainable is the supply chain system. In order to construct a framework which is resembling as much as possible existing practices, what we want to do is to incorporate state dependence into price, schedule, demand, and also dealing with uncertainty. In particular, we want to make sure that the price that is charged by supplier is really depending on how fresh the product is, with the idea that a fresher product can be charged a larger price relative to a product that is close to expiration. And of course, whether or not the good is fresh or close to expiration might be information that is not always available in the supply chain network system. And we also want to look at the demand of retailers. With this demand, we want to make it also depending on the state. In particular, we want that demand depends on the freshness of the good that is being supplied. So if a good is fresher and is not overpriced, typically there will be higher demand with respect to a good that is almost close to expiry. And we also want to account for effects which depends on seasonality and also on the characteristics of the product. And because this is essentially designed, this research is designed to to shed light on what would happen during periods such as the COVID-19 pandemic. The key word of this pandemic is uncertainty, right? We have uncertainty about everything, about when restrictions will be lifted, when the economy will be reopened. And we don't know, for example, when the good is being delivered, whether or not it will arrive on time, because there are typically substantial delays in delivery due to several different forms of breakdowns that can happen along the way, or changes in policies and so on. This basically means that one is to construct a careful stochastic demand model. Now, the other objective, of course, this is like a broader research agenda, and this is what will be developed during this year, like as a part of the project. Now I want to discuss some preliminary results that we obtained, and these are also these are results that we have also partly developed over the last summer, not this summer, but summer of 2019, in collaboration with Chandra from IBM and the former student Umud Asaba. We looked at the serial supply chain system where there is a supplier and a retailer. So this is a very stylized framework. There is only one supplier and the retailer, but it's essentially a first proof of concept that we can use to build up more sophisticated model. Now, the supplier is replenishing its inventory from a perfectly reliable single source. So there is just one single source that is providing goods. The good, there is a single good in the model, and this has a life cycle of H periods, which means that after these H periods, the good will expire and there will be no salvage value. So it will be worth nothing, which means that it has to be consumed somehow before its expiration. And we are thinking of a system where retailer and supplier are using a first in, first out inventory issuing policy. So the first item that goes into the queue is also the first one to get out of it. And just to give an illustration of the structure, we have essentially a lead time, and there is quantities that are somehow varying with respect to the echelon where we are in the supply chain system. So first, like the reliable source is providing good to supplier, and the supplier is providing good to the retailer, and the retailer is finally giving the good to the consumers in the market. And there will be a lead time in the transmission from the source to supplier, and in the transmission from the supplier to the retailer. And also what will be important to determine when and how to reorder is the in-transit inventory. So ITS is the inventory in transit from the source to supplier, and ITR is the inventory in transit from the supplier to the retailer. And then we have the total inventory, both for the supplier and the retailer, which includes both in-transit inventory and the one that is already available at the supplier and at the retailer. Okay, so now the question is, should we share or not share information, and does information sharing help? Like in this simple model, we look at a BT, which is a key quantity, which depending on whether or not we use blockchain will be shared or not. And this is the minimum remaining lifetime of the inventory of the supplier before the retailer places an order in the period T. Now, traditionally, if we don't use the blockchain, this value of BT will be unknown to the retailer. So this is only private information from the supplier. The supplier basically knows what's the remaining lifetime of his inventory, but the retailer doesn't. So what does the retailer do? He can implement a reorder point policy. He can say, okay, I will decide to reorder based on a heuristic rule, based on a specified rule, which cannot be based on the value of BT. And the rule that we have considered is basically the following. We say that when the on-hand and in-transit inventory, which is denoted by IPR, is small enough, smaller than a specific threshold, R, superscript R, superscript small r, then the retailer will basically make an order in order to ensure that in-transit inventory is again above the reordering point. So it's basically a policy where you try to be conservative and you don't want your in-transit inventory to be too low. And the same will be applied for the supplier. So the supplier will also apply a similar policy. Now, what happens if we allow to share information? Then in that case, the retailer knows the value of BT because he can look into what's the inventory of the supplier, and therefore he can know how long it takes before the items will expire. And of course, this information will be then used by the retailer to design his reordering policy. And for example, the retailer strategy now can map from BT, which is this minimum remaining lifetime of the inventory, to the reordering point. And intuitively, what we expect is that if BT is small, so if there is a small, if the remaining inventory has a low lifetime, then the retailer will find it profitable to set the reordering point low, in the sense that he wants to start reordering soon. He doesn't want to wait too long before reordering, because basically it could happen that he will get only goods that are spoiled, goods that are already in the expiry stage. And in this specific framework, we have done some preliminary analysis. We have first looked at the Nash equilibrium of this game. We can view this as a game between firms, and each firm is trying to maximize its own profit. There will be retailer, there will be again the supplier and the retailer. And we looked at a set of experiments based on various combination of all the input parameters, which are like the reordering point and again, the remaining lifetime of the inventory and so on. And basically, we looked at goods that have long or short life cycles. So this parameter H, which captures the expiry date, can be large or low. How variable is the demand? Is it high or is it low? And how about lead time, like for the good to be transferred from one side to the other, right? From retailer to supplier, from supplier to consumers, and so on. And this corresponds to operational characteristics, which are typical of many short lifetime goods. For example, if we think about meat or seafood or fresh produce, these are all very sensitive to the expiry. So if you don't deal with these goods soon enough, you will basically not be able to capture anything out of it. And here are some preliminary results. We looked at average performance metrics. So we did a bunch of Monte Carlo simulations, and we looked at the statistics of these simulations. In particular, the focus is on comparing what happens when there is no information sharing versus what happens when we share information via the blockchain. And we looked at the percentage change between the variable of interest under the information sharing and without information sharing. So the percentage change basically is always completely relative to the case where there is no information sharing. So NIS denotes no information sharing, and IS denotes information sharing. And we have seen that the spoilage here occurs when the good expires before it's being sold. And if you look at this table, I just want to point your attention on a specific quantity, which is the percentage change in spoilage. So what we see is that when we use information sharing, when we use the blockchain, then the retailer is benefiting from knowing the inventory of the supplier. So it's benefiting from knowing the remaining lifetime of the supplier's inventory, and in fact, he sees his spoilage being reduced by 0.21%, but this comes at the expenses of increasing the change in spoilage for the supplier. So the supplier is basically bearing all the costs of spoilage. And of course, this is a model that it still misses or still lacks of a clear trade-off, which is what we want to incorporate as a part of this project. We want to design mechanisms, first of all, that enhance sustainability. Typically, the producers want to have the good out of their hands as soon as possible. So they don't want to deal with goods, they want to get profits out of it and then pass the cost to others. And the question is, what happens if these costs are shared through the blockchain platform? And this is essentially designing a mechanism that ensures a cost not to be just sustained by one entity, like we have seen in the previous table, where all the costs are being passed by the retailers to supplier, but basically sharing the cost in some way and providing incentives so that everybody's willing to take a part of those costs. This problem is very important, especially in light of the COVID-19 crisis, because we are seeing firms cutting down on their production substantially, and also because they are cutting down on their production, they want to sell goods which are outdated or close to expiry as soon as possible because they want to be profitable. And of course, they don't have a lot of workforce because they are cutting down on the workforce. And what we want to do in the future is precisely to design these profit sharing agreements so that both the retailer and supplier have their incentives which are aligned. So they are both happy of sharing this cost because each of them would basically no incentive to deviate from this policy. And the idea here is to basically analyze situations where they are willing to share this cost. And in particular, one way, for example, of achieving that is to somehow provide incentive to retailers, or force retailers is a bit a strong word, but essentially make sure that the retailers are willing to purchase goods, even if they see that these are close to expiry. Because if they, at the moment, if they see that they're close to expiry because they can look at the inventory of the supplier, they will not be willing to do that. But if this is the case, again, the costs are always on the side of suppliers. But if we can design incentive schemes so that retailers get somehow compensated for purchasing goods which are close to expiry, then we could see that there will be some agreement, some sharing of the cost or sharing of the profits. And the conjecture is that the spoilage rate will decrease under these profit sharing agreements, and we should see that the aggregate profits, where we look at profits both of retailers and suppliers, so the welfare of this economy should go up.
Hi, my name is Steve Rogers. I hope everyone is staying safe. And I'm the Vice President of Blockchain Initiatives for Supply Chain at IBM. And I'd like to share with you a practitioner's view of blockchain. So the first thing I'd like to point out is that blockchain is not the end all, right, to all problems, right? It is one of several technologies that are really transforming supply chain today. Hybrid cloud is giving us the ability to deploy infrastructure very rapidly. AI can make sense of massive quantities of data and convert them into actionable insights. Robotic process automation is eliminating a lot of the manual tasks that we perform. But if your goal is to securely share business information across enterprise boundaries, that is where blockchain comes in. One of the things I wanted to do is talk about the fundamental elements of blockchain, right? They're really four. The first is the shared ledger. It's different than historical shared databases because it's append only, can only add to the string of data, and it's immutable. You cannot go back and change anything. You don't write over something, you add something to the ledger. The second is the consensus process, right? The main goals are to keep the multiple copies of the ledger in sync, provide evidence if one or more of those copies were tampered with, and act as a key step in verifying transactions that they're legitimate before you actually record them onto the various ledgers. The next one is smart contracts, which is the ability to run automated programs which execute when certain conditions are met. And lastly, you can actually control the visibility and the actions of the different participants in the network, which gives the founders of the network, a very important control over what happens within the solution. The promise of blockchain, that's what I like to call this chart, it saves time because you're no longer having to deal with intermediaries that are building that trust for you. It is a peer-to-peer network. It removes costs because you don't have to pay those intermediaries, as well as you can eliminate all those areas within your company where data is being disputed, whether it's system to system or your company to another company. It reduces risk. There are a lot of forms of risk, but to me, the most important one that blockchain addresses is the fact that if anybody's node in the network is hacked into, I never say blockchain is unhackable, the other nodes in the network will identify that. It is tamper evident, and that's very important because it allows you to take corrective action. And lastly, it increases trust, right? And it does that because, if you are all looking at the same data, you're all participating in the approval of the transactions, how does that not increase trust? Okay. So my next chart talks about where I actually see this being used in the supply chain in industry today. 4 major categories: shared visibility, tracking, an asset through various different processes performed by different companies; provenance, who did what, when did they do it, and what authorizations did they have to do it; dispute resolution, which is all about having one set of data that we look at. So I'm not disputing whether or not that invoice is actually payable at this point in time. And lastly, identity management, whether I'm a person, a corporation, or even an IoT device. Am I who I say I am, and can you trust my information? There are 3 fundamental ways to bring blockchain to market, 3 business models, if you will. You organize an industry group for the betterment of all, and you collect contributions to fund the development work, right? Secondly, you can integrate blockchain to existing product offering. That's really advantageous because then you don't have to build the network. It's already there. It's all the users of the product. And then lastly, if that doesn't satisfy your needs, you can bring a solution to market with a few other industry leading partner companies and then recruit others to join. And ways to fund that are charging transaction fees or charging subscription fees. Okay. So the 4 key messages of blockchain-based solutions, or what I would say is my personal experience over many client situations, is first make the decision: do you want to build something? Do you want a custom home, or can you live with something that's already built? Do you want to join a network, right? The second is, and it goes right back to that first one, is you have to understand that convening a network is as much work as the development of the solution itself. Why is that? Because blockchain is a business transformation. It's not an IT transformation, right? Thirdly, every participant that you want to join your blockchain network must have a value proposition, or they will not join. As a matter of fact, if they think it will disintermediate them or actually hurt their business, they will fight against you. And then lastly, and this one is you have to experience it to really see it, is that once platforms are in place, there is a tremendous opportunity for innovation. And when we get to the Q&A, I can give you some really good examples of that. But my last chart is a little bit about the blockchain maturity model, which is when you start out with that first project, your minimum viable product, you must be thinking about your minimum viable ecosystem. Who are you going to get to work with you, right? And that is an IT project because usually it's proving the technology. But if you look at all of the key elements under the pilot and then the production, you will look at those terms and you will say, whether it's the funding model or whether it's the governance model, right? How are you going to recruit members? Who's going to own what IP? Those are business issues. And that's why I say this is a business transformation. So I'm really looking forward to the Q&A, and I'm open to any and all questions that you might have. Thanks very much.
Hi, I'm Eran Tromer. This is an overview of the course Blockchains and Their Applications, taught by Alex Biliris and me at Columbia University in fall 2019. Blockchain technology was popularized by cryptocurrencies such as Bitcoin and has since expanded to be a promising and powerful technology in business, finance, law, and other areas. This course covers blockchain technology in a comprehensive, systematic, and interdisciplinary way. It surveys major approaches, variants, and applications of blockchains. Beyond a solid grasp of the principles, the course aims to build familiarity with practice through numerous case studies, as well as hands-on projects. The topics covered include, first and foremost, disentangling the myriad aspects of the blockchain concept. We provide a requisite cryptographic background, and we discuss the enforced semantics of assets, scripts, and contracts. We discuss state consensus, such as mining and Byzantine fault tolerance. We discuss deployments, such as coin creation and forking, as well as many applications. We address scalability, lightweight wallet protocols, and similar. We discuss trust, privacy, and zero-knowledge proofs. We also discuss specifically Hyperledger's architecture and applications. Beyond the technical aspects, we also spend some time discussing regulation and taxation, trading, and markets. We had 4 guest lectures, including 2 from IBM Blockchain Solutions and IBM Food Trust. Last semester, 26 students completed the course requirements, final exam, and 2 group projects. The first project focused on surveying selected topics, such as the Lightning Network as a scaling solution, arbitrage bots, a survey on blockchain storage, decentralized exchanges and investment vehicles, as well as legal aspects like the right to be forgotten in an append-only world. The second, larger project focused on designing and building new systems. Students proposed and prototyped blockchain-based solutions for image storage, dating, a machine learning marketplace, as well as work contracts for vulnerable migrant workers and management of professional identity using self-sovereign identity. These projects and more were designed to demonstrate a comprehensive end-to-end synthesis of the applications, including motivation, background study, design, execution, and critical self-analysis. All these projects were presented in class, which provided valuable, teachable moments to discuss advanced topics, as well as to revisit typical failure modes, such as security and privacy concerns. Overall, the projects demonstrated effective assimilation of the concepts and techniques presented in class, as well as familiarity developed with development tools and application frameworks. Several students expressed intent to continue their projects beyond this class. We look forward to teaching this course this year with improved COVID-compliant pedagogical aids and updated to reflect the state-of-the-art and industry in the rapidly evolving area of blockchain technology.
Hello everyone, my name is Sinand Iyer, co-founder of ProducePix, and today I'm going to talk about our journey through the Columbia-IBM Blockchain Launch Accelerator. Where produce is farmed and where it is distributed from can be thousands of miles apart, and a weakness in our current food supply chain is the inability to track its quality as it goes from farmer to distributor. This leads to conflict between farmer and distributor over the quality of the produce as it could spoil during its journey. ProducePix is an app that allows users to evaluate the quality and freshness of produce. We use human-integrated AI to quickly evaluate quality, thus helping resolve disputes. Before we continue, I want to talk about who we are. I am a graduate of Columbia University. I received my undergraduate computer science degree in 2019 from the Fu Foundation School of Engineering and Applied Sciences. It was through my undergraduate experience that I was able to get involved in this accelerator. My other co-founder is my father, Sridhar Iyer. He has years of extensive experience in the food supply chain industry. The produce industry is one we interact with on a daily basis. After all, it is how food gets from a farm to our plates. The industry loses 5% of all annual revenue due to food spoilage. It may take 4 days for a strawberry to go from a farm in California to a distributor in Chicago, while its shelf life is only 12 days. Over the course of transportation, the quality of the produce may change. Farmer says produce is grade A when shipping, but it's only grade C when it reaches the distributor. What ProducePix does is allow tracking of the quality of produce over the course of its journey. Rather than having a USDA inspector who can be subjective, as he or she is a human, we use an AI algorithm to assess the quality of produce. We are the first and only app that utilizes barcode and the image of produce. This will help estimate produce quality and the potential remaining shelf life. Now we have a short video that further explains how ProducePix works.
At every point along the supply chain, the app takes a picture or pictures of the produce inside the box and the barcode outside the box. Images are analyzed using an intelligent image processing platform to ensure consistency. Disputes about the quality of produce are common. We use an intelligent, human-integrated AI platform that lets buyers and sellers inspect the produce through video conferencing. We also provide real-time language translation.
We're extremely excited about the progress ProducePix has made, and a large part of that has been due to our selection for the Columbia Launch Accelerator in partnership with IBM. Coming into this accelerator, we had this idea for a blockchain-based product to help optimize food supply chains in the United States. We felt that this accelerator would be a great opportunity to explore this idea further and build a business out of it. Entering the accelerator, we wanted to create a platform for smart contracts between farmers and distributors. We hope to gain valuable mentors in the blockchain space as neither of us had too much expensive experience in this area. And finally, we were excited about the opportunity to build and grow a business plan. Some key points from the accelerator that we will go into detail are the access and mentorship from IBM, meeting with the blockchain expert attorney, and access to the Columbia Digital Storytelling Lab. The law firm we were introduced to was nice enough to connect us with not only an attorney who has expertise in blockchain, but one who has worked with USDA procedures before. The workshop led by the Storytelling Lab helped us divide a pitch for the final demo day and also how to just present our company and ideas in general. We also got to meet a lot of exciting companies in the accelerator and learned a lot from them. The connection with IBM proved to be extremely valuable during the accelerator. They provided us with a lot of information about blockchain and gave us generous cloud credit we could use for development. We also got access to mentors who were able to guide us in various stages and aspects of developing a business. Looking back on the program, we found it to be extremely valuable. We got a better understanding of the exact technology needed in our product and how to go about executing it. We also learned valuable lessons about launching a startup. The workshops on customer acquisition and slowly developing a business class were invaluable. Finally, we were exposed to many leading figures in the blockchain space who proved to be valuable contacts. Finally, I would like to thank Jack and Dimitro for all the support they provided over the course of the program and for organizing everything. Through the accelerator program, we were one of 3 companies to receive follow-on funding. Furthermore, earlier this year, we were selected for the GS1 Startup Lab. GS1 is an international standards body for barcodes. We also participated in the Cambridge Venture Cafe Seed program, which enabled us to work with a large produce retailer in the Northeast, namely Ahold Delhaize. We have our test app available and are working with clients to launch the final product later this year. For those interested in learning more, feel free to reach out at ire@producepix.com. Thank you.